Hello. So to continue talking about sound, we're going to talk about sound waves through this Google slide, and I'm just going to, you don't have to do anything to it. We're just going to walk through it. But the one thing I did want you to add to your notes is that a sound wave is a longitudinal wave as well, which I can't say. It's just one of those words I can't say. So I'm going to write it on my paper, but I also want you to write that. Just write it at the top, and please write this on your notes that it is a longitudinal wave that Miss Connor can't say ever. I don't know why I can't say it. Okay. So just make sure to write that down so you have it. All right. So a sound wave is a movement of air. It has to move through a medium. And yesterday I said, not yesterday, earlier, I said that sound has to have a medium to go through. And what a medium is something that it can travel through. It's something that is in the middle of the sound wave working, getting to us. So a medium would be matter. So it has to go through solid, liquid, or gases, and it moves the best through solids. All right, so how is sound made? So the longitudinal wave, the vibrations move the air, and the waves disperse that way. So they come out from the source of the sound, and they come to your eardrum. And if you notice right here where we talked yesterday that the where the sound waves bunch up, that's called compression, and where they break apart a little bit and they're not as bunched together is called refraction. And then from one top of one wavelength, that's called the crest, to the other is called a wavelength. All right, so sound waves. It's a pressure wave. They push stuff out, which we're not going to talk about that. So, like I said, they move the fastest. Sound waves move fastest through solids, then liquids and gases. And also remember that sound waves travel in all directions. So something I think is cool is that higher temperature causes sound to move faster because higher temperatures have the molecules inside have more energy. So if you think about boiling water and how fast that water moves compared to ice water or ice. So hot things move, the molecules move faster. So sound travels better in hot conditions. We don't need to do that. We don't need to do that. So decibels is how sound is determined. So they always say like the decibel scales. So like the threshold of hearing is at 0, and like the regular just being somewhere in a classroom would be 35 decibels, and then 120 is when it's like super loud. So if you look, a rock band concert is at 110, and 120 is where it like hurts your ears. So that's pretty loud. Yeah, so we'll just move on. All right, frequency. This is a low frequency, okay, because there's not, see how the wavelength would be pretty far apart, but this is high frequency, okay? The wavelengths are very close together. And that has something to do with the pitch. So high frequency, high pitch. So this is going to be like this. This is high frequency, high pitch. And this would be low pitch because it's very low. So that's the difference. High pitch, high frequency. Low pitch, low frequency. So we don't really need to talk about that. Okay, let me move on to this one, which I think is super cool. Okay, so I love this diagram of this wave because it sort of shows you how the sound wave actually moves. And this part right here where it's bunching up, that's called compression. And then it becomes refraction. Compression, refraction. Compression, refraction. And if we were in the classroom right now, I would have you put your hands together, like barely touching, and that is compression. And then you would pull them apart, and it's called refraction. Push them together, it's compression. Pull them apart, it's refraction. Okay, so the transfer of energy from one place to another. So if you watch that sound wave, that little dot is just traveling, 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 traveling. He's eventually going to get over there, okay? Yeah, see that little red one? He's eventually going to get over to the other side. He's just a going. Okay. Sound wave, they wave by compressing the molecules. Compression, rarefaction. Compression, rarefaction. Compression, rarefaction. Compression from here to here, okay, is a wavelength. So here is our wavelength graph. So from here to here is the wavelength, okay? The top, where one crest is to the other is a wavelength. From the bottom is the amplitude, how loud or soft something is. So this would be a very loud sound because it's a big amplitude. Okay, so again, the height of a wave determines the volume of the sound. So when the crest of the waves go out more, it's louder. So amplitude determines the softness or the loudness of a sound. So see how it's smaller here, that's going to be a quieter amplitude. This is bigger, it's going to be a louder amplitude. Amplifier, so yeah, I didn't think about it that way for some reason, but guitars, and if somebody plays guitar, or you like rock music or country music or any kind of music, they use an amplifier when they play guitar, and that amplifies the sound, that makes it bigger. Okay, so frequency can also be shown in a sound wave. So remember that when it moves faster, when the wavelengths are closer, that's a higher pitch. And when they're further apart, it's a lower pitch. Oh, goodness. Okay, so just another picture again of a quieter amplitude, louder amplitude, lower pitch, higher pitch. All right, we don't need to do that. So remember what I said earlier, that vibrations of the matter is what causes the sound. And when you're in, hot weather, the vibrations are faster. All right, which sound wave has the highest frequency? So which one would be the highest frequency? The highest pitch? Well, that would be number 4 because the wavelengths are closer together. Which sound would have the lowest frequency? Which sound would have the lowest pitch? That would be 3. Highest, lowest. And then it would be 4 would be the highest, then it would be 2, then it would be 1, then it would be 3. Okay, so just look, comparing 2 and 3 even, the wavelengths are shorter. There's less distance between the two wavelengths right here on number 4 than there would be on number 2. Okay, let's look at this. So we've got our line in the middle. This one is not as far away from the center line. This one is further away. So then this would mean that this line, it has softer amplitude. The volume of the sound is softer. And this one means that the volume of the sound is louder. I hope I just didn't burst your eardrums. Okay, so again, let's look at these. So let's think about these wavelengths. All right, well, this has what kind of frequency? This is probably like a normal frequency, probably right here where my voice is now, but it would also be pretty loud because it looks like the amplitude is pretty loud on all 3 of these. So the frequency would be about, well, I guess it would be a little lower. Probably right here is where the frequency is, the pitch. This one would be right here. This one would be right here. I hope your parents listen to me, and I'm sure they think I'm crazy. Okay. So you are going to read a small passage next, and then you are going to be done with science. Goodbye. Let me know if you have questions.